begin. Yeah. This will probably also go on YouTube, just because why not? I'll probably stitch up multiple streams and they'll go on YouTube. Yeah. So, yeah, thing we're going live, right? Let's see. This, yep, we're live. Nice. So, what we're doing today is the question. That's the real question. So, I will be reviewing a vulnerability. CVE-2022-32250. Yes. I'll mainly be looking at this write-up of the vulnerability and trying to basically understand it. And yeah, this is probably gonna be today's stream. Today I'll be going over the KASLR part, because that's like, I think, the most difficult thing in actually when you actually want to explore the vulnerability. And it's in this vulnerability specifically, not usually. Usually it depends on the vulnerability, right? And new primitives, etc. So yeah, I'll be going over the KASLR leaking part today's stream. Maybe I'll have one more stream where I'll go over the actual path override so we can escalate our privileges, and then I'll probably try to replicate their exploit, which I looked over it. What is this? What happened? Huh? I don't know what's happening. Yeah, I looked over their exploit. It's not that complicated, so yeah. And I have some experience with netfilter vulnerabilities and their exploitation, because I already looked over this vulnerability and I wrote a write-up on it, and then the proof of concept, an exploit. What is happening? Do I have to actually log in? Oh shit. Does it force you to log in now? Or is it just fucked? Let me see. I don't know, I'm not logging in. Okay, so yeah, that's basically it. I have like experience with netfilter vulnerabilities. So yep, be looking over this one today. Yes. What is it? 2 viewers. Unlikely that they're... Oh, it says unstable. Average stream bitrate too high. Why? It told me... this should be fine, right? Is it actually unstable? Can I limit it without actually stopping the stream? I think it should stabilize, because my internet is pretty good. Like, my connection should be very good, like half a gigabit. I think this should be fine. Yeah, okay. So basically what I've already looked over is the general vulnerability. We'll go over it in a second. And then I looked over the way to actually leak the heap address, which is actually pretty simple. Leaking a heap address is very simple. Yeah, okay. So the vulnerabilities are used after 3. When you allocate a lookup expression in netfilter with non-anonymous set, which however is not stateful. You don't set the stateful flag. So basically, they're like expressions. I don't probably, if anyone is watching this, they probably don't have much experience in netfilter. Maybe, I don't know. But like they have expressions in netfilter, which is the Linux firewall framework, and they have expression actually in NF tables, which is like the subsystem, which is like deals with the firewall and routing and etc. Yeah. So they have expressions in it, and those expressions can be used to form rules. Rules like if UDP port is like 400, allow or drop the packet, or etc. etc. So yeah, that's how expressions are basically used. Expressions form rules, and yeah. And what we have here actually is we have an expression which is the lookup expression. The lookup expression is used to check if a certain value, for example the value x, you see one stable? Yeah. Oh my god, it's bad. Oof. Maybe I'll start recording it in case it's very fucked up on Steam. I don't know. So I can actually upload it. Yeah. I don't know. I hope it's good. Hope it's not too fucked. Yeah. So basically it's used, the lookup expression is used if we have a value x and we want to check if a value x is in a certain set. And what is a set? A set is basically a collection of values, of keys and values usually. So for example, they can have like, let me see. For example, it can have like, you can have key x, value y, key x, like value y, typical key value store, right? And a set is basically a structure in NF tables which contains those. It can also be used to like as a collection of, for example, ports. If you have a certain, when you're building like a firewall, and you want, for example, to drop all packets on port 130, 145 and 166, 45 and 166, you can use a set for that, where you just define the keys. And the lookup expression then can look into a set that you have defined, and can check if a certain, if for example the port of the current packet that's being handled is in this set. Basically, this is what it does. It's very simple. Yes, and yeah. So this is what the lookup expression really does. Yes, here we have here it's like how it's allocated. For example, this expression init is being called every time an expression init is being called every time a new expression has to be initialized into the subsystem. It basically parses it to netwing attributes, allocates it in GFP kernel space, which is pretty important for like use after free vulnerabilities, where it's what flags are being used when it's allocated and stuff because of the slabs, you know. Yeah. And then it calls another function. It tries to initiate to a table to initiate yes, to a table, and that's pretty much it. This is what this function does. Basically starts the initiation of an expression. This actually adds it to, this actually finishes up somewhat the initiation of a general expression, and it does it by calling the expression specific initiation function, because every expression has like a different initiation function. I think I covered it here. Yeah, every expression has a different initiation function. For example, the immediate expression, which is just used to load certain values into the netfilter subsystem, has NFT immediate init, which is called when you add this expression with a val, right? And so it calls this specific expression specific function here, and then it goes on, right? And this expression specific function for the lookup expression is NFT lookup init, and this actually allocates the lookup expression. And we can look at the lookup expression. Let's actually look at it. NFT lookup. It's here. The structure itself holds a set, a pointer to a set. I think I have it here actually somewhere. Yeah, but we'll look at it in Boolean, just because we can actually click and we can, yeah. It has a pointer to a set, and as we already said, a set is basically a key value store, a very complicated key value store, but it's essentially a key value store, even though it can be used for different purposes as well. But it's a key value store. This is a set instance. It points to a set instance, which is actually the set instance we'll be conducting our checks in. We'll be looking up into this set, it has a source register, which basically means from which register in from which register in netfilter or like NF tables we're going to be comparing. What are the registers though? There's a very simple concept. They're basically 16 or 4 depending on what size you're using. They used to be 4, now they're 16. And they basically are like 16 4-byte with like registers basically, where values are stored. And they can be viewed as a continuous buffer with that has just like 16 offsets, or they can be viewed as like separate registers. Yeah. So for example, the port is in register 4. It's not by default in register 4, the port of the incoming packet, but you can save it in register 4 using another expression. And then if the port is like 145 and you want to compare the port that's in register 4, if it's in the set, you set sreg to the value of register 4, which is this nft reg 3204 basically. Yeah, like 03 technically, because it starts from 0, but yes. And direct will contain then the verdict if it's, so if we're looking up, if this is a key we're looking up, the direct will contain the this is a key, it will contain the value. Invert is basically inversion, instead of like key value key. And a binding is basically a little structure that is used to bind this lookup expression to the set. It's kind of weird, but we'll look over that. What is this? This is the set, and it basically has a list head, which is like, no, just it's a ring twist, obviously, and holds a pointer to the chain. This is the chain in which the expression is allocated, because they're in netfilter, they're like chains. I recommend Nyaku before, like, if you're watching this in a video and not on stream right now, I don't think anyone is watching it on stream, to be honest. Yeah, if you're watching this in a video, what I recommend basically is to just go over this article I've written. It's a relatively good introduction into NF tables and everything I'm talking about. So yeah, even though it does not cover the the lookup expression, so I might actually extend it to cover the lookup expression as well. Yeah, basically contains a pointer to a chain, and chains in netfilter just like linear lists of rules that are executed one after the other. So for example, first check the UDP port, then first check the port code, then check the port. If it's UDP port, that's like a chain, and you can jump between chains as well. Yeah, and then we have flags, which not so important right now. So this is a binding. Whenever a lookup expression is initiated, it is binded to the set that it's going to be looking up into. So here we can see bindings, and it just binds it to like this set. Yeah, but it's simple. So we have this lookup expression. This is what it does. It basically looks into a key value store, and it says you're basically looking for like a key, and it returns the value. Very simple. Yeah. This is what the lookup expression does. Now, if you're looking how it's initiated, we basically can look if no source is provided or no source register are provided, just return error, like, yeah. Then tries to find the set here, or sets up a set, yeah, tries to find it and returns it, gets the flags from the binding, and then attempts to bind the binding to the set. This is what this does. And this is the function that is being called here. This this like NF tables bind set. It binds it, and you can see how it binds it. Here, this is the important part, right? If the list is not empty. Wait, what is it? Wait. This compares if it's not empty and it's anonymous, just returns an error. And then we have this here. So that means that if our list is, for example, empty, but it is not anonymous, it won't return error. Or if it's empty, or if it's like not empty, but it is anonymous, it still won't return you know. But we'll basically use non-anonymous sets. Yeah. And this is how it actually binds it. It just binds the chain, like it sets the chain in the binding to the current chain where we're adding it, the CTX, the context chain, and then just uses @tail_assume to just add it into the linked list. Pretty much that's it. That's it pretty much. Yeah, and then ups the use count, the set use pointer, counter pointer. Yeah. And so this is the function that actually calls the first function we've looked over, which basically initiates every expression. This is the function that allocates it, like allocates everything. And we can see here that if an expression is not stateful, if an expression's flags are not, so an expression is not stateful, it will send us to this. Like it will go to the error set element expression, which will destroy the expression, and destroy it just freeze it and calls the destroy function of the expression. And the destroy function is expression specific. So for example, the immediate expression has a NFT immediate destroy. So here, if we look at the lookup destroy function, it just destroys the set that it belongs to. However, what if the set is a named set, right? Well, basically, it only destroys the set if it's anonymous and it's empty. But what if it's not anonymous? What happens then? Then it won't get destroyed. However, it destroys it, but it does not handle the fact that it already added it to the bindings. Because what it actually does, it calls the init function here, which calls the table at the new expression function, which calls the lookup init function. So it already added it to the bindings, it added it to the set bindings. So even though it attempts to destroy the set, it cannot destroy it because we're not going to be using an anonymous set, we're going to be using a non-anonymous set. It cannot destroy it. But what it basically does is it gets a user after free, because it frees the expression here in the destroy function, it frees it. But it cannot destroy the set, and it does not remove the binding. So it's just the binding remains. So now in the bindings, we have a pointer to a segment in memory, in heap memory, that is already freed. So it's a use after free. Yeah, that's pretty much it. That's the vulnerability. Yeah. It's not a difficult vulnerability, even though you have to have like a lot of knowledge about NF tables and netfilter to actually go into it. Yeah, if I didn't use this vulnerability like a month ago, the other one, the CVE-2022-32250, I would not be able to understand this one. So yeah, netfilter is a little bit complicated. Let's say that. Is anyone in chat? It says one viewer, but I think that's me. I don't know how Twitch works. Yes. Let's actually now go into exploitation and how that could be exploited. So we basically have a segment in memory, which, like segment, that's not really the right word. We have like an object in memory, which is being free, but we still have a pointer to it. Which means that if we allocate something of a similar size there, now we have a pointer to a structure which we should not be having a pointer to, basically. And let's see how this could be exploited. We're first going to be looking into how we can leak a heap address. This is covered here in my notes. Right. Let me just think a little bit of chocolate milk. Yes. Is my audio on? I really hope it's on. Yeah, it says. Maybe I should play some music. But not here. No, but actually. Okay. copyright music, not copyright music, I mean copyright music, copyright free music, YouTube. Let's see. What film? What is this? Happy upbeat. I don't know about this. We're gonna leave it in the background for now. Oh, maybe. Do this. So it's like quiet, you know? Yeah. Okay. So, the one thing we have to take note here is when this expression is allocated, it's allocated with the getFreePage flag kernel. Which means when it actually, like, if you take a look at the slab allocator flags, I don't know if they're here. No, they're not here. Here. Nope, not this one as well. Sorry. This one. This is way too loud. Can I like? Yeah. Yeah. The getFreePages flags. The kernel one is the one that's most commonly used. So yeah, here it's basically, this is like the documentation of the memory allocation of KMalloc and the flags that you can use for different like slab allocators, like different like slab caches. Are they called caches? I think so. Yeah. So any expression that will be overwriting over the freed space has to also use GFP kernel. So the most commonly used message struct, which basically just holds a message, like. And by the way, this is not like, this is basically all notes which I made reading this write-up. So I'm just like recounting or like going over the write-up right now, just through my notes. Yeah, I'm not like coming up with it myself or something. It's just the write-up. Yeah. The message structure is just like a message structure. Ring twist, type. Yeah, and pretty much, and just the message follows immediately after this. Yeah. However, the problem with this is that when you come here, you have to look where it's being allocated, which I think this one allocates it, right? Yeah, it's being allocated KMalloc, but with a different flag, the kernel account flag, which means it's accounted for in C groups. Basically, you can look this one yourself, but the accounted flag means that it accounts for it in C groups. So if they have like limits in, or like not segmentations, like if there are limits to C groups of different resources, it accounts it in this. It's not like global in a way. I don't know if that's the proper way to explain it. Probably not. I think that's very scuffed. But yeah, let's look at C groups, the control groups, the Linux kernel. They account, measure a group's resource usage, etc., etc. So the accounting flag basically accounts for it. Yeah, in a C group. So obviously we cannot use this one because this flag uses a different like slab than the GFP kernel. So we cannot use it because they won't be allocated. It cannot be allocated in the same space that our NFT lookup expression was allocated. So we could not exploit the user after free using message struct. However, if you use the user keyrings and you use the user key payload as a primitive, you can see that it's being allocated to the GFP kernel tag. This is what they do here as well. Maybe there is also like different structures, which of course they are, which we could use as primitives, which being also allocated to GFP kernel. But I'm just going as R in the write-up. However, which one allocates it? Let's see. I don't quite remember. Might be this one. Of course, GFP kernel here. But what is the mark? I don't know. Here in the write-up, I think they had a thing on it. Yeah, it's being allocated by user prepass. Let's take a look at the user prepass. Nope, not the prototype. Defined as a function. Yeah. Here, kmalloc, GFP kernel. So we can use it as a primitive basically. It's a key payload. Now here we have to do some maths on how how much space the lookup expression takes, and how much this is going to take, and what actually we're going to be able to like influence if we allocate it over the freed segment in memory. So this is the lookup expression, right? This is a structure which holds it, but actually this is not what's allocated. This is what is This is what is allocated. The NFT expression structure, which in itself in the data parameter contains the NFT lookup. This is the expression agnostic basically function. Every expression is not function, structure. Every expression is being allocated to this structure in memory. Yeah. Ops basically holds the operations, that point to the operations. And what are the operations? Operations are just a structure which holds like these functions for the certain expression. Like the expression specific function, like evaluate, the initiation function, activation, the activation, the story, etc. etc. So this, how big exactly is the NFT expression? Well, first we have a pointer which is 8 bytes, and then we have a data like parameter segment which is aligned 8 bytes. So it actually depends on what the expression we're allocating. So looking here, we have already 8 bytes here, and we have 8 more bytes for this set pointer, and then we have 1 byte here, 1 byte here, 1 byte here, 3 1 bytes, 1 byte allocation, 1 byte parameters. Someone. We have already what is happening? Oh no, I can hear myself. Okay. And at the end we have a binding structure, which in itself contains a list head, which is 2 pointers, next and previous. Then it contains a chain, which is 1 pointer. So here in the binding, this is in total how many bytes? So I have 24, this 5th. 25 bytes here in the binding. And yeah. So as you can see, we have first 8 bytes. So that's 8 plus 8, 16, plus 3, 19, plus 25. 44, but I don't think my math is good. I think I'm missing something here. Okay, let's see. Let's first, I'm skipping too far right now. Yeah. First, let's look at the user key payload, which is our primitive. It contains a FCU head, which is 2 pointers, 16 bytes. You can look at it in bootn. bootn. What is it? Oh. I don't think it really matters. Just click on any of them. Wait, what am I looking at? Why is there no definition here? Testing. Oh. Because of this. I missed. No? Might be a little bit dumb right now. What is happening? What is the member? What is the actual definition? I'm just click on 1 second. Okay. Point is, I looked into it yesterday. Why am I? Wait. Yeah, it's the same thing. Oh, I remember. This I think is covered in the write-up. It's actually a callback head. Yeah. So the actual symbol I think is, yeah, the actual symbol is callback head, which contains 2 pointers, as we said. Oh, it's here, the 2 pointers. Sorry, not here. Yeah. And they're aligned to the size of void. Yeah. So 2 pointers, 16 bytes. And we have data len, which is 2 bytes because it's a short. So 18 bytes here. We have 6 bytes alignment because this needs to be 8 byte aligned. So it gets 24 bytes. So this can only read and write 24 bytes from the start of the actual segment that it's allocated into. That's very important. Right. So this means that if we take a look at the NFT expression, because we have 8 bytes here, 8 more bytes here, 16, 17, 18, 19. Then we have, because it needs to be aligned 8, because those 2 are pointers here in the list, we have some alignment to bring it to 24 to 24 bytes. So actually, what happens is this data here, the data part of the user key payload, can read and write from the start of the binding, the set binding. So we cannot touch the source register, deregister, like freed stuff, freed like space, but we can from the bindings. So this can be used to leak a heap address, obviously, due to the fact that the bindings, they hold next, this is a list head. The first parameter in the binding is a list head, linked list, which holds a pointer to the next and to the previous one. So if we allocate a single like lookup expression, which is going to be destroyed immediately after that because we're going to allocate it without the stateful flag, it's going to be freed, but it's not going to be removed from the bindings of the set. Then if we allocate the key payload in its place, now the key payload can directly read and write on the binding, on the list head here. So we can read and write next and previous pointers. But the problem is that we have only like one expression, one binding in the set. So we need to actually, to the same named set, add the second expression. And now the second expression will be linked to the next pointer in the binding, in our first object. It's a little bit complicated, not even, but I just by explaining it. So now when we allocate the second lookup expression, if we actually read the list head of the first expression which is freed, yeah, you actually get the next pointer, which points to the second expression, but it's a pointer. So if we read user key payload, if we read the payload here, we'll actually get a heap address. We'll be able to leak the heap address of the second object. So pretty much what we do is we use after freed object 1, we allocate the user key payload on its place of the appropriate size. We use after freed the second object, but to the same name it said, And now what happens is the second object is pointed to by the next point of the first object. So now if we read user k payload, we'll be able to read the pointer that points to the second object from the first object. And this pointers, but it should be like. So actually what happens is we'll get the address to the second object and we'll be able to read the heap address this way. Yeah. Took me a while to explain it, like 35 minutes. But this is basically bringing you up to speed. Like anyone who's watching it in the video, if someone is going to watch it, it's bringing you up to speed to what I did. If this is very hard to understand, you could maybe take a peek at the actual write-up by Teorio and my article on netfilter, which basically is an introduction to expressions, registers, the basic like building blocks, the hooks of netfilter, etc, etc. Yeah. So you're basically up to speed. I won't be writing the exploit for the to which we'll be making the heap address now. What happened with my music, by the way? Oh. Okay. But I might be writing it next time. So we have the. Now we're going to be looking into how we can read KASLR. I'm not even sure how much we're going to be looking into it. Because I think I have to go in a little bit. But we can take some peeks into what's actually says in the write-up. I'm not even sure how I'll be leaking a KASLR address with the primitive we have. Like, what could we leak actually? I don't know. But they did it, so. Yeah. So basically, we say that the MQ function is suitable for exploitation. It manages multiple messages. Let's actually take a look at it, because I haven't much experience with it. Interesting. The MQ multiple messages are managed by POSIX message 3 node. What is this? What are those config files? Huh. Okay. The POSIX message 3 node. RB node. Maybe I should open it into a different tab actually. What the fuck? To use RB trees, you have to implement your own insert and search cores. This will avoid us to use callbacks and to drop the automatic performances. I know it's not the cleaner way, but in C, not in C++, to get performance and genericity, yeah, something. I have no idea what RB node does. What are those? Parent core, right, left. The fuck? Are they quarks? Okay. What are avoidant black trees and what are they for? Avoidant black trees are a type of self-balancing binary search tree used for sorting sortable key value data pairs. Okay. This differs from RX trees, which are used to efficient store span surveys and hash tables, which are not kept sorted to easily to to be easily traversed in order and must be tuned specific signs and has function where arbitrary skill occasionally storing arbitrary keys. Okay. Interesting. Windows arbitrary implementation lives in the file. To use it, the Linux arbitrary implementation sometimes speed. Yeah. I don't care. I want to know how it works. Okay, so we have a left and right branch, doesn't make a tree. Balancing by the research. Okay, I don't think this is that important, but okay, I got basically what it does. So this has a heavy node. It's a linked list and has a priority. Fine. This is the function which allocates them. What? It calls them leaves. Interesting. So every tree node is called a leaf in here. Interesting. Okay. It's allocated in KMark 64. Every tree. This is long. How much was that unsigned long? 64 bit. Is it 8 bytes? 64? What? Okay. What the fuck? Fine. Okay, it's game log 64. I'll have to look into it, I guess. And it's implemented as follows. Ivy node. Oh, okay. Is 24 bytes. So the message list next has an offset of 24 bytes. Interesting enough, same as our binding, which also has an offset 24 bytes. Okay. Hex 18 is 24, by the way. Yeah, not sure what we know, but just accounting. Okay. So our tree node the Abbey node is 24 bytes. So this is at offset 24. Okay. Cool. In the figure below, you have 1 and you have 2, which are the lookup is after feed, like objects, expressions. Expected each, the data contains, yeah, we already went over this. If we allocate UF1 and UF2 in particular order, they will connect as shown below. It's kind of lucky, to be honest, that the offset is the same. But yeah, we override this basically allocated at the same place as the first is after feed object by using this function. Okay, fine. I actually have to look into more into actually how the occasion happens, how the coring happens, etc., etc. And then we write this is interesting. It says write UF1 binding next equals to UF2 binding and create UF2. Why would we be doing that? By default, if we have allocated 2 objects, the second object is, and they're into the same set, you could do expressions. The first allocated expression in the linked list holds like a pointer to the second one in the set because they are binded like linked list. Huh. So I don't quite get this part here. Right, UF1 binding next equals to UF2 binding. I don't get that. Why? Why would we need to do that? I guess because we're overwriting with this. Yeah, perhaps. So, but can we? It's fine that we're overwriting, but how can we actually write UF1 binding next to it pointing to UF? I guess if we just no. Oh yeah, wait. Yeah. If we just allocate a second expression, which is going to be used after feed, it will be set. There is head of POSIX message 3 node next will be set to UF2 binding. So this I think should actually be the reverse. You first allocate UF2 here, which does this basically, because the set and the bindings in the set, they don't know that this object UF1 has been freed, so they will just overwrite the offset 24 the next pointer, which funny enough is also a next pointer in the POSIX message 3 node. So I think it's supposed to be, I don't know if maybe they meant something else, but that's how I understand it. You first allocate first object, you overwrite, then you allocate the second one, which will make the POSIX message 3 node list head next point to the UF2 binding, and then you overwrite UF2 with structure or user key payload by using the key steal function. Okay. If I understand this, I'm not quite sure why we're doing it, but okay. Let's see the graph. I'm just gonna hovering here from time to time. No one is messaging. I don't think anyone is watching. Which is funny. But I think I can check in here, right? Users in chat. Some users. I don't know. Okay. I hope if anyone is watching, I hope it's like at least a little bit like informing or fun. I don't know. Probably not, but it is what it is. Is there more? How can I find? I want something that's like. Oh, I really like this one. It's no copyright. Nice. I really like this one. Okay, we're playing this one for like 2 minutes and a half. Okay. Should I update my notes now? Nah, we're gonna be doing it later, that's not fun. I'll do it off stream, I guess. Okay, let's see. So this here is the Abbey node. They said it's hex 18, 24 bytes. So it cuts off somewhere here. Wait. It cuts off exactly here. This is now. Never mind. It cuts off here. True. It's 3 words. And then this is the next pointer, which points to your plus 18. And this plus 18 is just a binding. So that's cool. Plus 18 is data 0. So this will actually point to data 0 here. Cool. We have that. Nice. So the next pointer of the POSIX message 3 node will point to the data segment of the user key payload. So, yep. Cool. Okay, if I understand it now. In this case, message list next of stock becomes UF8 message is connected to and what? POSIX becomes UF2 plus 24 and message list connected to stock message list. Therefore, data in UF2 is the same overlap with struct message. What the hell? Wait. How does the POSIX message 3 node work? The message list, it points to the next, but the list head should point to just point to the wait. Need a real bed to think. Sorry for the coughing. Yeah, that is true. It points to this. And messages connected with the fuck? Is that how the POSIX? Oh, okay. I need a little bit of research to do here. I think I have already this somewhere. There is a message list. Fine, but this list head also points to like another list head. This is the right up of interesting. I want more music. I don't know what this is. It's the same guy though. Stop playing it. Three node. What does it point to? What the fuck? Why does it point to a message structure here? The POSIX message 3 node. Is that how it works? Are there like references? Wait. What the fuck? Just this one thing is it. Okay, I'll search in this file because it's the only file that uses it. I think I'll just search in it, post it, and I'll look at all the leave parent. I have been on fine message insert. So the way it inserts it is by adding a new leaf, and IB entry it just adds the entry there. How does the IB entry function work though? Where is it? Am I blind? Oh, it's here. Type member. Yeah. So the type is posting message. What the hell? Then why would it point? Is there something I'm not understanding? Like obviously, but what is the? MQ has a function that manages multiple messages. They are messaged by a twin node. This is the message list. This is the head. So can we just assume? No, I don't think that's a good assumption for me. Never mind. They basically say here that the message list next, this, will point to this, right? And therefore, and message is connected with a struct message list. Why? Like, message does have a list here as well, but they basically say, I mean, maybe that's how it works. Maybe that's how the POSIX message tree node works. I thought the POSIX message tree node in the linked list just points to another POSIX message tree node, but I don't think that'll make much sense. I basically thought that the way they allocate is POSIX message tree node, and under it there is like the actual message struct. But what they're basically saying here is that POSIX message tree node just points, is just next with like the beginning in the linked list, that the linked list is actually made of message structs, which kind of makes sense honestly, but I need to see some data, some proof, you know. This is indeed how it works. But and the problem with the kernel is it's like undocumented, like almost entirely undocumented. Like people from time to time write like comments and they're like, yeah bro, it's documented now. No, it's not. What do you mean? It's undocumented. And we don't have the guy like for the Linux kernel stuff. What is his name? From the Windows kernel. Windows kernel guy. I don't know. Doesn't matter. I forgot his name. I think he's dropped something maybe. I don't remember. The guy who just documents everything in the Windows kernel. Like he's like the Wikipedia for the Windows kernel. Yeah. Okay. It's actually this function. Maybe I should take a deeper look into it to actually understand what is happening. Oh, yeah, my headphones disconnected for a second. So if there was like bad audio because of that, or like you know, static. Okay. So this function, do message queue, timed send. Message queue destination perhaps? This? No clue. Message length. First I have to allocate memory before doing anything with existing queues. So it allocates the new leaf. Okay. It initiates the list head with new leaf message list. Okay. And then info node cache new leaf. A new leaf with sorry to no. But basically this is the list head, the message is there, okay. So now I very much like to know how it handles the messages. I don't know what the fuck I'm looking at. What is this? Adds message to the queue. Save our speculative allocation into the cache. Height ones. Some height one stuff here. Have pipelines. I want to look at this function. What does it do? It takes a message and inode info. What is this inode info? What is this? It holds the message to inode is the node cache here. So when they're talking about node cache, this is actually the leaf here. Cool. I understand now. I understand. So this function here, it goes somewhere inside message. Look at inside message info, queue size list, add there, and adds it to the M list to the message. Adds the M list to the leave messages. So they are right. Okay, this is cool. I understand it now. I understand what I'm talking about. The POSIX message 3 node is just the head. And the linked list doesn't contain more POSIX message list heads nodes, but it contains messages. Cool. So actually, what I'm talking about here is that this thing would point to like this, but this, it will be treated as a message from down here. Like this will be treated as a list head of a message. And as we know, if we look at the where should I open it? Here, I think. If we look at the message, the list head is here first, then we have a type, and then we have an actual message that follows. So actually what happens here is this is the list head, right? And if we look at the list head, here in the types, it first is the next pointer and then the previous pointer. So actually this would contain a pointer to the next one, this to the previous one, and yeah, they say it here. And this is to MTS, and MTS is something, I don't know, something. The same type and MTS. Yep, that's cool. That's really cool. The message text size. MTS is the message text size. Cool. So I understand this. That's really cool. Damn. I think I want to write this down actually, because it's really cool. Maybe. Maybe I should do it after that. I don't know. But I'll just write some notes, real quick notes down right now. Then I'll off stream how it form it into something better. I'll copy this here. Some quick notes. Looking at which function did we look at to determine what the fuck is happening. This one. No, doesn't this one. Fuck. Where did it go? Oh, this one. Message insert. Message insert. We see that POSIX message 3 node is just the head of a link, or the beginning of a linked list, and the linked list is formed of the list heads the list head instances of messages. Cool, very nice. And now we add this real quick here. C and this mlist is pointed to by nah, this doesn't. Yeah, some quick notes on how multiple messages are handled in a linked list. It's just the beginning of a linked list. So basically, POSIX message 3 node is just the beginning of the 3. No, what is the right? It's the root. And every instance in the linked list is a message after it. Okay, this is pretty much how multiple messages are handled in the linked list. This is cool, very cool. Maybe drop even here. Wait, no. I'll probably like drop the POSIX 3 node and RB node stuff here, just because why not? Just so I can have it in my notes. Okay. Cool. Software coughing. I'm going over now. Cool. And not a single message in the chat. Oh my god. Cool. Okay. Damn, I'm learning so much from this write-up. What is the title? Going over... I forgot what I said it to. Going over the CV, doing some research. A little bit... What did you say? A little bit sick today. Okay. Fine. Yeah. Cool. So how do you actually exploit this? This is cool that it treats it as a list of messages, and we can then basically control like the pointer to the next message. So we can, but how? What do we do here? How is that actually exploitable to leak an address? Like so we can defeat KASLR, you know? According to the structure of stack message can be modified. However, in the case of copy to user, it's impossible to copy more than the slab size currently KMLX64. Therefore, KASLR is leaked only when appropriate structures are allocated below UF. Eh? What do you mean below? What? I don't like when people just say below, because you can look at like memory different ways. Like, it's not stack memory, it's heap memory here. So I guess, yeah, doesn't matter. But yeah, Um, Accordingly, the structure of statements can be modified, however, in the case of copied user, it is impossible to copy more than their slab size. Okay, mark 64. There are 64 bytes. Oh, there's a vulnerability. Wait, interesting. Let me read this real quick. Observed system due to issue it. Okay. Like, kmark 64 just uses 64 slabs. Byte. 64 byte slabs, right? I'm not actually very well learned into the sub allocator stuff. That's why I actually favorite this one. I might go over it again. I'm not actually sure when it allocates, like, for example, a 64 byte slab, right? Like, it's just the data that we can use 64 bytes, or is it with the metadata 60? Yeah, it has to be the metadata 64 bytes, because the slabs are powers of 2, right? Yeah. Heap, actually, heap object metadata. The implementation, like, I don't remember what it was. I haven't done heap stuff in a while. I don't remember exactly. They were like 3 words, like 2 words metadata. I think they were 2 words. Therefore, KASLR is leaked only when appropriate structures are located below. You have to. I don't know what they mean by that. What the hell? Let's look at the actual. I guess. Nope. I want to look at the actual way it's copied user is implemented. No. How could I write this so it gives me the actual definition? What does copied user return? It returns copied user. It returns a pointer, right? Copy a block of data into user space with s checking and it returns an okay, fine. Forget that. 2 from the user space with less checking. This is, yeah. 2 from inside log n. Numbers of bytes to copy. Okay. No. This tab allocator is way too complicated in a way. I don't want to have this stuff. I just want to find what I need. I want to see how subsets structure the message. Linked lists. As far as I remember, swaps are like full pages of just like semi-initiated objects ready for use of like a certain size. Right? I think so. Hmm. Why did we? It's okay then. Came out 64 because if this is 18 bytes, this is 2 more bytes. 20. No, this is 24. This is 2 more 26. No, not 2 more. I'm dumb. This is 24 bytes. This is 2 more words. 16. So this is 40. The integer is 4 bytes. So 44. So it's indeed KMalak 64. Okay. Fine. Because the next 5264. Possible to copy, but it's not. So we're basically looking for a kernel address, for like a .text address or something? Something to defeat KASLR, which is under UF2, which was how many? It's like 38, like 40? This is like exact 64, what do you mean? Oh, yeah. Wait. This is like 16 bytes, yeah. This is 64. So we're looking for something to be here. So you can actually leak it. It needs to be in the 64 byte binary, is that correct? Maybe. Not so sure. We'll see. What is happening on my screen? Why is it? Yeah. Previously, struct per CPU reference data was used for the case of KMalak 64. I don't know what the message security stuff does. We'll have to check it out. 1 bytes of power. Field points to Canada. That's the exploitation, I think. There. Huh? No? Located by. It is freed by. Received. Let's see. So it holds a pointer to some allocated. What? Allocate the composite message blob. Allocate the IPC blob for all the monitors. Interesting. Unfortunately, K3. Oh. Does it just allocate some random ass stuff to make sure that it can? So it tries to free it after that. It tries to free something, and if you Wait. Maybe it doesn't work like that. I was thinking about that. It could be like it allocates something, stores it in the security parameter, and then before it actually uses it, it frees it to make sure that it's intact, or like an address that that it can be freed. I don't think so. But still, what? Oh yeah, but it does do that. Because now the problem is that I think this is exactly what it's used for. Because this now points to here, and it thinks it's a message structure, even though it's a user key payload structure. Because here we're basically saving a user key payload, right? But it believes that it's a message. So it tries to free security first, which is allocated somewhere here, right? It says at some offset, I don't know what. And if it cannot free it, then, well, an error is thrown. And there are no cache costs, yes. If the subpath is allocated below. Oh yeah, this is exactly what I'm talking about. If the structure per CPU rev data was used for the KASLR leak, unfortunately it does the K-free thing, and what it happens is to try to free, for example, the count here. The cache goes because there is to free count, and it can't free it. So yeah. So they're saying that we use a key payload to do it. Again, somehow. Interesting. In struct user key payload, RCU head exists. RCU head is a structure designed to wait for critical section to be terminated. When the critical section is terminated, the callback function RCU func is called. RCU head stores another RCU head address at the next pointer. Yeah. Therefore, if the chunk exists before a KASLR leak can be performed. How? I'm a little bit confused on how. Struct RCU head is a structure designed to wait for a critical section to be terminated. When the critical section is terminated, the callback function is called. RCU head stores another RCU head pointer. Let's play something. This is a mix. I only hope it's. Oh, it is. No, this is not. Fuck. This is definitely not. Well. We're playing Fuse again. I like Fuse. Yeah. I'm not completely clear on how the KASLR leak will be performed. Oh, I got it. Fuck. Is this a pointer to a function? A callback function. RCU function is called. So actually, a callback head. Oh, I got it. In the user key payload, the RCU key payload, the RCU function thing, that's a pointer to a function. So we just leak this one, and we get an address, text address. And if we get a text address, then yeah. Okay. Cool. The function do message queue timed receive is used to be inside the MQ. Do message queue timed receive calls message get to get structure message get. Message get refers to leave node to get the first message and calls the list del to link the first message from the linked list. Afterwards, store message executes copy to user to send the data. Then free message frees structure message and message security. KASLR leak is possible because message data contains a function address. Okay. We need to read this like 10 more times. But it doesn't seem that complicated, honestly. Is this team going well? Dropped frames. Okay, not that many. Yeah, it's fine. Everything is fine, I think. Okay, time to take a look at this function. I think what it took like 10 looks at it. No, not this one. Yeah. Oh, it was this one. Was it? I don't know. Doesn't matter. Do message queue timed receive. I guess. Fine. Message insert wants us to have a valid spare node stuck so it doesn't have to KASLR GFP atomic allocation, but it will fall back to that if necessary. Oh my god. Okay. So what are they talking about? The function is used to read the stuck message and send the MQ. Calls message get to get the stuck message. Okay, let's look at the message get function and what it actually does. What does it cover though? This initiate this hit. Store message. We have here store message. So what does it do? Message get. Oh, it does here. I saw it. Fuck. This is not what I wanted to be. Yeah. Message pointer. Message get info. So it gets. Heh. It gets the first one from the info. Because the info just holds the POSIX message 3 node. So what does it actually do? Message get. Yeah. MQ node info which holds the POSIX message 3 node. Oh my god. Okay. During insert, low priorities go to the left and high to the right. When receive one, the highest priority is first, so look all the way to the right. The fuck? Okay. So it just returns a message. Gets the first entry, the list. Leave message list, okay. Gets it from the list. Then removes it from the list. Pretty simple actually. Okay. So this function just gets the message, removes it from the list, etc, etc. Yeah, and goes to this deal to unlink the first hub. Afterwards, store message executes copy to user to send the data. Does it do that? Let's see. When does it do that? Oh, store message here. If return is 0. Huh. Okay. Store message. This is called. Okay. Let's see. Why does it always give the prototype on top? Oh, I don't need a prototype. I almost always need the actual definition of the function, not a prototype. Yeah, that's called copy to user. Cool. fine. That is what happens. Then free message freeze. Oh yeah, we must not forget about this. Free message is called. Free message is called, which actually frees. Does the security message free? Then freeze the message. How is that going to be handled? That's a good question. Freeze the message look and message security. However, message security actually has to be like something, you know. We should not be freeing like random pointers because that will throw an error. So how do we make sure that it's actually something? Not really sure. I just like to switch between screens a lot. Yep. Dun dun dun. Okay. Stack message and message security. This thing's the message. Right? How many? I have to take a look. Message. And see what the security is. Okay. So we have this, which is 8 bytes. The MTS. And it's like 2 pointers down from MTS. Okay. Here they said MTS is 3, so it would be 5. So it'd be right immediately after it. What the hell? Because 4 is next. And it would be right after it. So how do we make sure that this here, right after the UF2, isn't actually something that we could free? How? Oh, yeah, right? Wait. What we do is we allocate a third user key payload using a third UF ID stuff, I think, and it's no, it's not that. I was thinking about no. I'm kind of sick and getting stomach pains. Oof. If the user key payload is immediately after it, and it is the first thing after it, to be the callback hit, the next pointer, and that could be freed, so that could work. I have no idea what the next pointer points to though. I have no idea, like, no idea. So, yay. But at least it won't arise an error, I guess. So that's fine. KASLR leak is possible because we then will be leaking the function here. Right? Yeah. Because let me think. Okay. So I'm muting myself. Just, yeah. Coughing and other sounds around the house, you know. Need to be like that sometimes. Maybe I'll just make myself quieter so you cannot hear it. Yeah. I hope I'm not too quiet. But, yeah. Okay. That should be fine. So, we're leaking. We can only leak KASLR 64. Here, we're using a user key payload. It points to this. This points to this. And now, I had figured it out like 10-20 minutes. So I just forgot my visualizations because I'm not writing stuff down because it takes a lot of time on stream and it's kind of boring if anyone is watching. So, yeah. The same list just points to other stuff. My brother is home and he just returned from his basketball, like, what is it called in English? I don't know, basketball training. And he's hyper active right now. So he's screaming. Love that. Okay. Malcolm, I kind of, I don't know what the hell. The problem here is that we can only copy to user KASLR 64, and if we copy KASLR 64, if I guess if it thinks this is the mlist head, then it would copy like 8 bytes including this one down. Oh wait, no, what the hell? Wait. No. If this is the head, then 2 here is m-type, 3 is MTS, 4 is next, 5 will be security, which is going to be an RSU head. So that's not a problem. It can be freed. That's good. So no error will be thrown there. And then the final yeah. And then the word right after this one here, which is the 5th word, which is not displayed right now. The 6th, which is going to be under here, is going to be the function here, which is going to be a text address. So that's how we make it, I guess. So because this key payload here is a message, it will start it, and if we free it and copy it to user, it will start copying after the header, and the header ends at data. So we have data. This is wait. As we said, this is data 3, 4, 5 after data 5. So this is 5. So from here down, it copies. And the fun thing is that data 5 is actually the thing that's this thing. This is data 5. in user key payload. That's what it matches to. That's what maps to. If we have it allocated right under it, because then data 5 here will be RCU next, and right, and data 6, which, as we said, if I said it correct per Malcolm, this is 3, 4, 5, 6. The data 6 stuff is going to the function. So 5 here is the security. It thinks the function thinks it's security, but what it actually is the next in the callback here. It can be free though, so we don't care, because that won't raise an error. Fine, perfect. And then data 6, however, it thinks it is the start of the message, because the header just ended, because the header ends at 5 here, and it thinks it's the message, and it starts copying it to user, but what actually is that's where the function starts, the pointer to the function. So what we print to, what we actually copy to user is not a message. It thinks it's a message because we've pointed it to think it's a message, but actually copies to user is a pointer from the user key payload RCU callback head. So perfect. So basically we lie to the function by the way we structure our stuff. We basically allocate a POSIX message 3 node here, which makes the function, which is, where is this function? What was it called? I forgot, and I can't find it. Do MQ time to receive. It thinks that the pointer that's located at the 4th word in UF1 actually points to the first message, but what actually points to is user key payload. And this user key payload has right under it allocated another user key payload. And when it starts reading, because it's a message, it goes out of this. It goes out of this here. And here data 5, as we already said, it starts thinking it's security, we free it, it's actually the next, and then the next one thinks it's the actual message start, because we fooled it to think it's the actual message start, but actually copies to user a text address, which allows us to defeat KASLR. Cool. That's really cool. Okay, so the stream, basically, to find out, to summarize what I had done and find out how to leak KASLR, took like an hour and 42 minutes. I might spend the next 20 minutes to actually write down my notes on how the fuck is actually done. And I might do it on stream, because why the hell not? You know? Yeah. Okay. If someone is watching, let's check. If someone is watching, it says some people watching, but I think that viewer, commander, I think, like just bots, something. Okay, yeah, that's definitely a bot there. If someone is watching, just might not be a bot, but I think they're like that type of bots which go on streams to, like, you know, yeah. I'll up my volume a little bit again. Yeah. That's probably terrible for people who are actually just deaf sound. But yeah. Okay. Okay. So in the first UFI, so over the first UFID object, we allocate POSIX message 3 node. It is the root of a linked list of message instances. The wrist head, I'll just copy this. Copy these two. This was of size 0.18 equals 24 bytes. At offset 24. At offset 24, is located the pointer, the next pointer which points to the first message. Luckily for us, at point 24 in NFT expression slash I don't know how to in NFT lookup NFT I don't know how to write it down. The expression slash NFT lookup is the next pointer which points to the next binding. So in this POSIX message 3 node instance that we have allocated over our first UFID object, the next will point to our second UFID object. There, over our second object, we are going to allocate what are we going to allocate? Use a key payload. Okay. Why is this function? I want just to copy the name. Now we are going to use to actually, what's this call? Actually calls this function though. I have no idea. What is happening with my PC? Why is it slowing down this much? The fuck? Oh, this is the call. Fine, no. Based. Then we use to actually weak the message. Use a key payload. Let's see how user key payload header or extract overlap is that the word? Yeah, with message struct. And here I'll have this one and that one. Opa. Oops. Okay. So I'll just here. It's actually pretty important that we here also have the avcu information, which I'm going to copy from the write-up here. I like streaming just for one reason. I feel like I don't distract myself. Like, I don't have ADHD, but if I did, like, it neutralizes it. Because I cannot just open YouTube and start watching random shit, you know? It's good for my productivity. So this is 20 word 3. Fuck, how do I actually type this one out? How do I write it down? They have like a schematic which helps you to understand it. How do I do it with text information here? I think the actual way is here to write it down. So this something. No. To actually leak the message. Wait. No. We allocate the user key payload there, which points to payload. The I have to wait. The message list.next points to what did it point to? It points to this here, which is data 0, I guess. Points to the key payload. However, here there are some caveats. Do MQ timed receive freeze a message struct security. That means so this parameter must be a real pointer. There is a caveat. No, there are some caveats actually. There's another one. We can also copy the user only up to 64 bytes. Up to the slab size. It's here like KMalloc 64. No more than that. So what we need to do is allocate a second user key payload right under the first one. Message struct. Thinks message mlist next. Is assume next. Thanks. Oh no, button. It's the opposite. Wait, it thinks is message dot mlist dot next. It thinks that m type that avsu actually this is irrelevant here. No, it's not. It thinks that m type no, avsu dot func is message m type. things. See? No, that's not correct. What the fuck am I writing? That's not correct. Oh my god, it really is not correct. Oh wait, I figured it out. Put him out and just, yeah, I just wrote it down wrong. Oops. Yeah. Oopsie. Oops, oops, oops. Why am I writing RCU here? That's not RCU here. It's user key payload. Oh my god, I fucked it up seriously. Okay. We'll just copy this graph just because it's so, like, it's actually needed to understand what is happening. Okay, good. It thinks data 0 is next. It thinks data 1. Data 2. We have data 2 here. Dot ts is message mts. It thinks data 4 is message next, message next, and it thinks, wait, now we do this, now we go to the next user key payload, allocated right under it. It thinks, I think I'll add this just because in Markdown it needs to. It thinks RCU next. RCU next is message security. This is why if we free, this is why when the function performs key-free security, it will okay, let's see here. Free name, yeah. And now it thinks also, it thinks that RCU func is message is actual message data 0. So if we copy the user the message, we will we will actually be copying the user key payload of the I think this is not entirely correct here, but it's de facto correct. I think there'll be like some metadata in between because it's like different heap like allocations. That doesn't matter. This, I think this from 0 will be 3 actually here. Actual message data, the RCU function here won't be at 0, but it'll be at 3. But this is not really that important. I don't think so. So for the notes, I'll leave it here because it's more like more obvious, you know. So if I copy to user, the message will actually be copying to the message will actually be copying to user key. okay, is the AVSU func of the second user key payload, which is actually a text address. So text address. So this is how we defeat KASLR. And this is some notes here that we have. I'll leave it here, but I think I'll delete this. Or like, oh, yeah, it's fine. So let's go over the. So first to allocate POSIX message 3, it is root of the linked message instances. Then at offset 24 is allocate the next point, which points to the first message. Okay, the first is lookup is the next pointer, which points to the next binding. So in the POSIX message, the instance that we have allocated over our first view of the object, the next will point to the second view of the object. Nice. Over our second option, we're going to allocate user key payload. Now we're going to use do MQ time to save to actually leak the message the message. That is actually user key payload. The message of this next points to data 0 of the user key payload. The message this next points to data 0. True. So it thinks that the first message, the key payload that we have allocated is actually its first. Actually, message struct. Okay. However, there are some caveats. Do MQ time to receive frees message security, so this parameter must be a real pointer. We can. Another problem is that we can also copy the user only up to the slab size KML64, no more than that. So what we need to do is allocate the second user after the first one. So right after UFI, like this. Let's see how user key payload struct overlaps with message struct. It thinks data 0 is this stuff. This. So if we copy to user, the message will actually be copying it. This will be a new line, I think. So if we copy to user, the message will actually be copying what we'll actually be copying is the AVSU func of the second user key, which is actually a text address. So this is how we defeat KASLR. Okay, I think I updated my notes. This is pretty good. This pretty much explains. I think it's 2002 minutes. In 2002 minutes, I went over the defeating KASLR of this setup, which is like pretty significant. If I was a bit more knowledgeable in how the message POSIX stuff works, it would have taken like probably an hour, but I had never like studied it before. So yeah, this stream was actually pretty informative. Just super like productive. It would have taken me like 5 hours to actually, or like 6 hours to do it in my free time, just because of all the YouTube that I'll be playing in the background, music stuff. So this is actually very, very productive. I might be streaming a lot more if it's this productive. Yeah. Okay. So I will be uploading the stream to YouTube. It's pretty informative. Yeah. Well, this is for me. We basically went over this entire KASLR about the setup with this vulnerability. And this vulnerability is very interesting. It's a heap vulnerability used after free in netfilter, and netfilter is something I'm exploring a lot in my free time, you know? So, yeah. Well, this is for me. Not chat message the entire stream though, but it is what it is. Well, bye.